In this video, we're taking a look at how to use the properties of Boolean algebra to simplify a logic expression with the goal of trying to implement it using as few gates as possible. So here is the expression that we want to take a look at. It's a function f of 4 variables a, b, c, and d. And the function has 1, 2, 3, 4, 5, 6, 7 terms in here, so a c naught d naught plus a c naught d plus a b naught c plus a naught b naught c d plus a naught c d plus a naught b c plus b c naught d naught. The first step is to use absorption, which means that we're looking for terms of the form x plus xy which are equal to x. That's property 13a in the Boolean properties in the book. And we're also going to try to use combination, the combination property xy plus xy not equal to x, property 14a, if possible at all. So in this particular case, we can see that we start out with a c naught d naught and a c naught d, so that's a place where we can use combination, and we can say that this is equal to a c naught. And then we continue scanning here. We have a b naught c, so we cannot combine that with the previous ones. Then we have an a naught b naught c d, so we cannot combine that with the a b naught c. But we have here a naught b naught c d and a naught c d. So here we can use absorption and say that that is equal to a naught c d. And then there are two more terms here, and it turns out they cannot be combined with any of the others, and you can also not use the absorption property. So at this point, we have the expression f equal to a c naught plus a b naught c plus a naught c d plus a naught b c plus b c naught d naught that we would like to simplify. So the next step is to try to use the consensus property and then to try to combine this with the absorption and combination properties to obtain all the prime implicants of the function f. So first of all, the consensus property, so that's of the form x y plus x naught c is equal to xy plus x naught c plus yz. And then second, prime implicants here. Okay, that's a term that we will define a little bit later on, but one of the terms here in the definition of f, for example, this a, b, not c, that is considered to be an implicant of the function, meaning that it contributes to the ones of the function. And if it is such that we cannot take off any of the variables here in one of those implicants without changing the function. So if, for example, we are going to make this ac and drop the b naught, then this is not going to be the same function anymore. And so that would mean that a, b naught, c is a prime implicant of the function. But if we can drop a term, for example, if we have a naught b c d, that is also an implicant of the function. It's one of the terms where f has to be equal to 1. And we can take here the b and drop it, a naught c d, and then we get the term that we have here. And so we still have a valid function here. It's still the same function f by dropping the b, and so a naught b c d would not be a prime implicant, it's just an implicant. So anyways, the goal is now to express this function f in terms of all possible prime implicants that specify the function, and that will actually make the function larger initially, and then to pick among those prime implicants and just to choose those which are necessary for implementing the function correctly. To apply the consensus property in a systematic way, we start on the left side and we're essentially marking one of those terms as our starting point, and then we compare this term to all the other terms and see whether we can use the consensus property to get an additional term in here. So for example, we have here between the first two terms, we have a c naught, a b naught c, so we have a c and a c naught, so we can use the consensus property between those two along the lines of c, and we can add a term a b naught as a consensus term. So this is consensus. And then we check whether there is any others. So we have a, and then on the next term we have a naught. So that we could use for consensus, but then there is also a c naught and a c. So the consensus term, if we were to take this one and this one, would be that, and we did it along the lines of a, would be to add c naught c d, but because of the c naught c here, that is equal to 0, and we normally do not bother writing those down. And then we keep scanning, so we have here an a and an a naught in the second last term, but we also have a c in here, so we have the same problem that we would get a c ended with c naught, and that would give us a 0. And then the last one, we have the common term is a c naught, so we don't have a term and its inverse. So comparing it with the first implicant here in this expression, we can only have one or only add one consensus term. Now looking at this, we can see that we are adding a b naught, and we also have a b naught c here. So the two things together here tell us that we are just going to use a b naught using absorption. So now we're going to rewrite the function f equal to a c naught, and then the a b naught c we replace by a b naught using absorption, and then we have a naught c d, and we have a naught b c, and we have b c naught d naught. And then we continue with the procedure. Now we are going to put our pointer to the second term, and we compare now the second term with all of the remaining terms. So we have here a b naught, and then there is an a naught c d, so we have a consensus term here of b naught c d. And we keep looking here. We have a and an a naught in the second last term, but we also have a b naught in that one here and a b, so that will give us a 0 for the consensus term. And then the our current term that we are using and the last term combined, we have a, then a b naught and b, so we can do a combination or a consensus term here along the lines of b, so we would have an a, c naught, and d naught as the consensus term. But we realize that we also have an ac naught term here, and so we use absorption to conclude that we don't have to include this term here. So now we have for our current function f, a c naught, and then a b naught, then a naught cd, a naught bc, b c naught d naught, and the new term here from consensus, the b naught cd. And now we're going to put our pointer to the third term. So now we're looking for terms here which have something where we can use the consensus theorem with a naught cd. So the next one is a naught bc, so we cannot use that one. Then there is b c naught, so we could use the c and the c naught, but there is also a d and a d naught, so that gives a consensus of 0. And then we have a naught cd with the b naught cd, so there's nothing to obtain a consensus term from, so we move the pointer to the next place here. And then we have a naught bc, and we compare that with the next term. So we have a c and a c naught, so we can use a consensus here of a naught, and then a b and a d naught. And then we compare our current pointer term with the last term. So we have a naught and a b and a b naught, so we can combine those. So we have an a naught and then the b naught, that's the one around which we do the consensus. And then we have cd, so we have a naught cd. Now checking here, we can see that we have that term already. So we are not going to add that because it already exists. And so now we can write our function as a c naught plus a b naught plus a naught cd plus a naught bc plus b c naught d naught plus b naught cd, and then our new term a naught b d naught that came from the consensus in this round. One of the things to point out here is that as you rewrite the function, make sure that you copy it exactly. If you miss one of the inversions here, or an a suddenly becomes a c or a d or something like that, then of course you're not going to get the right result in the end. So now we move the pointer to the b c naught d naught, and we check with the last two terms. So there is a b and a b naught, but there is also a c naught and a c, so the consensus would be 0 here. Then we have a b c naught d naught and an a naught b d naught, so we have a b and a d naught, so there is no consensus term here either. And then we move the pointer here, b naught cd, and compare that to a naught b d naught. So there is a b naught and a b, which we could use, but there is also a d and a d naught, so the consensus term here is 0. So we do have no more consensus terms to add. And in fact, it turns out that this is actually the representation of this function in terms of prime implicants. Okay, so in terms of our original idea of simplifying things, we have, of course, not achieved much yet. In fact, we have now a function that is more complicated. But it is a useful expression here. For example, if you have to show that two Boolean expressions are the same, if you bring both into the form here where all prime implicants of the function are listed, then you can compare them, and if they are the same, when all the prime implicants are listed, then you do know that the functions are the same. And if they are not the same, it's of course possible that you made a mistake. But if you did not make a mistake and the prime implicant expansion is not the same for the two functions, then the two functions are going to be different. So now how can we expect to simplify this further? Well, if you look at this function, certain terms are covered more than once. I believe here they are covered at most twice, but in general it could be that some of the terms could be covered 2 or 3 times. Let's look at an example. The term a naught b and cd is a term that where the function f is equal to 1. Okay, and we can see that in the expression up here, it is covered by a naught cd. Okay, that's this term here. That will cover the a naught bcd, because a naught cd and a naught bcd, we could use absorption and say that this is a naught cd, but we can also take a naught bcd and combine it with a naught bc and use absorption again to find that a naught bcd is included in a naught bc, and that's the term over here. So we are covering this twice. And the idea is now, in order to get from this sort of fundamental expression with the prime implicants, to get back to something that is simpler by using actually consensus again, but this time using consensus not to expand the function and add more terms to it, but by checking whether we can combine any two or possibly more of those terms in here and say that they imply another term. So that brings us to step 3, where we are going to simplify things now by dropping implied terms. And this is essentially a stage where we have to use trial and error. Computer-aided design systems do use either some systematic ways of doing that, for example, in the form of tables, but that actually gets out of hand fairly quickly for larger functions. So in practice, they do actually use some heuristic, which is something in between systematic exploration of all possibilities and using trial and error. It's essentially an educated form of trial and error. So here I have actually looked at the trial and error phase already, so to keep this reasonably short. So we're just going to take a look how things can be combined and discuss what some of the strategies are in general. So here we have a b naught, a naught cd, and we have actually already found before that this gives us a consensus term, and the consensus term is b naught cd, those two. And so what we are going to say now is that this term is actually implied. Okay, and so we're actually going to take this term and take it out. And that gives us the function f a c naught plus a b naught, a naught cd, a naught bc, and then b c naught d naught, and a naught b d naught. And we could now, for example, take a look at, let's see, I think the a naught bc and the b c naught d naught, that has a c and a c naught. So let's just try that here. That gives us consensus term, which we most likely did before as well. So that is an a naught b d naught. And so we could argue that then we should take out this term here. But it turns out that in this particular case that would be a mistake to do. So we cannot in general go and just look at the first kind of consensus term that we find and then just say, well, let's drop another one. Because it turns out this A naught B D naught is actually a very useful term to drop some other terms. And that's where the trial and error comes in, or the systematic procedure of making some big table that shows all the implications that we would have if we were to drop or include a term. So we're actually going to erase this here and not use this kind of thing, but we're going to go back now and we're taking a look at the first term and the last term. Okay, so we have A C naught, and the last term here has an A naught in it, so we can make a consensus term here, which is B C naught and D naught. And then we can see that this term here is implied. And again, we don't know necessarily from just having done this whether we should be able to, or whether it is a good idea to drop this B, C naught, D naught, because it might be that it could be combined with something else. But I tried this before, and it turns out it's a good idea to drop this B, C naught, D naught term. And so the next step then is look at F equal to A C naught, then an A B naught, A naught C D, A naught B C, and then we drop that implied term, and then we have A naught B D naught. And we're now actually back to 5 terms, which is what we started out after having used the combining and absorption properties. But the last term, if you check back, is actually now different from what the last term was in our first round. And now we find actually one more thing that we can combine. If you look at this term and this term here, then we have a D and a D naught. So we can add a consensus term here, which is A naught, and then B and C. And we can see that we have this term up here. So this is implied. And we take this one out. And we finally get the result that the function f, and now in its simplest form, is A C naught plus A B naught plus A naught C D plus A naught B D naught. So this turns out to be the simplest SOP expression for this particular function f. Notice that when we talk about simplest expressions, we would typically not factor out, for example, the A naught that is in here. So in principle, we could say that for the last part here, that this is equal to A naught CD plus BD naught. But we do not write things in this form normally. We usually try to bring it either into the form of an SOP or a POS expression, because those are standardized expressions that can compare it easily among different implementations or different minimizations. So keep that in mind unless it is specified differently. When we ask for a simplest expression, we usually ask for a simplest SOP, sum of products, or POS, product of sums expression.